Uh, Today we'll be discussing an important topic for JEE Advanced in ionic equilibrium, an important topic in ionic equilibrium, calculation of pH of an amphiprotic anion. This is another video in my series of videos in which I am taking up some important topics for revision for JEE Advanced. So today we'll be doing calculation of pH of an amphiprotic anion. What is an amphiprotic anion? Let us discuss that. Amphiprotic anions are anions formed by ionization of polyprotic acids. Let us consider a diprotic acid H2A. Diprotic acid H2A. On first ionization, it produces Ha minus. On second ionization, it produces A2 minus. It's the Ha minus that is amphiprotic. Amphiprotic can gain a proton, can lose a proton. Ha minus can gain a proton to form H2A. Ha minus can lose a proton to form A2 minus. So Ha minus is amphiprotic. We'll derive expression for pH of salts containing an amphiprotic anion and cation of a strong base. So let us consider the solution of a salt containing an amphiprotic anion and cation of a strong base, and let us calculate its pH. So we have understood what is an amphiprotic anion. Let us suppose that salt is NaHA. Salt is NaHA containing cation of strong base, that is Na plus, and amphiprotic anion Ha minus, and concentration of salt as equal to C. Concentration of salt as equal to C. We'll say that in the solution, resulting solution, concentration of Na plus will be equal to C, and concentration of Ha minus initially will be equal to C. NaHA salts will completely ionize. All salts are strong electrolytes. The salts on this dissolution will ionize completely. Whatever is the concentration of salt will be the concentration of Na plus, and will also be the initial concentration of Ha minus. Okay, Ha minus 0 represents concentration of Ha minus at time equal to 0. Now let us represent the hydrolysis and ionization of this Ha minus, the amphiprotic anion. Let us represent this hydrolysis and ionization on the left hand side of this board. The Ha minus will undergo hydrolysis. Ha minus plus water, it will give H2A plus OH minus. Its initial concentration is C. Suppose assume that degree of hydrolysis of Ha minus is H. So we get this as C minus CH. Concentration of H2A produced will be CH. Concentration of OH minus produced will be CH. Okay. The equilibrium constant for hydrolysis of Ha minus, we can write it as Kw upon Ka1. The equilibrium constant for hydrolysis of Ha minus, we can write it as Kw upon Ka1. Now writing the ionization of Ha minus. Ha minus can also lose a proton. In the first reaction, we have written that Ha minus is gaining a proton from water and releasing OH minus ions. Ha minus also behaves as an acid. It can ionize to lose a proton and form A2 minus ions along with H plus ions. If degree of ionization is alpha, then concentrations can be written as C minus C alpha, A2 minus will be C alpha, H plus will be C alpha. If you write the ionization constant for the ionization of Ha minus, this will be the Ka2 of H2A. This will be equal to Ka2 of H2A. Now, the H plus and OH minus ions produced by each of the above two reactions will neutralize. H plus and OH minus can combine to give H2O. We can write a reaction. The H plus ions combine with OH minus ions to produce H2O. So due to this neutralization, the concentration of H plus and OH minus will decrease from the values of CH and C alpha. They will no longer be equal to CH and C alpha at equilibrium because of some of the neutralization of H plus and OH minus. Okay, the equilibrium constant for this neutralization normalization can be written as 1 upon Kw. Now, before going into derivation of expression of pH, let us deduce an important result. An important result will deduce. With the help of that result, will derive the expression of pH. An important result which we'll be using here is the solution at all times remains electrically neutral. This is the principle of charge neutrality. The total concentration of positive charge in the solution will always be equal to total concentration of negative charge in the solution. We'll say that concentration of positive charge is equal to concentration of negative charge. Let us write the cations that are present in the solution. What are the different cations present in the solution? One cation is Na plus and another cation is H plus. These are the only two cations present in the solution. The total concentration of positive ions should be equal to total concentration of positive charge should be equal to total concentration of negative charge. Anions, क्या anions present? What are the anions present? Ha minus, A2 minus, and OH minus. We'll write concentration of Ha minus plus concentration of A2 minus. We'll multiply that by 2 because each of the A2 minus ion has a -2 charge. So total charge will multiply by 2, and then concentration of OH minus. Now, an approximation, what we use here is if the concentration of salt, the salt concentration C, it is not too low, it's not very low. Generally, it is greater than 10 raised to -3, greater than equal to 10 raised to -3. Then the concentrations of H plus and OH minus ions can be ignored. Yeah. So as this is a salt solutions are generally neither very acidic or nor very basic. So pH will not be very low or pH will not be very high, resulting in the concentrations of H plus and OH minus will not be very high or very low, will be in the range of 10 raised to -4, 10 raised to -5, etc. If concentrations of H plus and concentrations of OH minus are in the range of 10 raised to -4, 10 raised to -5, and the salt concentration is of the order of the value of C, Na plus is of the order of 10 raised to -3 and higher, then we can ignore the H plus and OH minus concentrations here. In this expression, we can ignore the H plus and OH minus concentrations. Okay. And such approximations are valid only if salt concentration C is generally greater than equal to 10 raised to -3. It should not be very, very low. So normally we talk about that its concentration should be greater than equal to 10 raised to -3. Okay. The exact value, the exact range will also depend on the K1, K2 values of the polyprotic acid, the diprotic acid, but let's not get into that. Okay. Normally, for all practical purposes, this will hold true. If salt concentration is greater than equal to 10 raised to -3, we can ignore the H plus and OH minus ions concentrations here. Now let us simplify this. Concentration of Na plus will put as C. Concentration of Ha minus will put as C minus CH minus C alpha. Some amount of H ionizes in the hydrolysis reaction, some amount of it dissociates in the hydrolysis reaction, and some amount of it dissociates in the ionization process. Plus 2 into concentration of A2 minus. Concentration of A2 minus is C alpha. Now, if we solve this, if we simplify this, we'll cancel C and C. 2C alpha minus C alpha will get C alpha. C alpha minus CH is equal to 0. Or we'll get C alpha is equal to CH. Or alpha is equal to H. So degree of hydrolysis is equal to degree of ionization, an important approximation which we use in this derivation of pH for an amphiprotic anion. The degree of hydrolysis is equal to the degree of ionization. Or we get the concentration of H2A is equal to concentration of A2 minus. काफी important result है. Concentration of H2A is equal to concentration of A2 minus. The concentration of species formed on hydrolysis will be equal to the concentration of the species formed on ionization. Concentration of H2A is equal to concentration of A2 minus. Actually, we have done an approximation. So actually we say that it is approximately equal, not exactly equal. The concentration of H2A is approximately equal to concentration of A2 minus. For a solution of amphiprotic anion, these two concentrations will be almost equal. Now let us derive the expression. We'll write the equilibrium constant expressions for the first as well as the second ionization, and we'll derive an expression for pH. We'll use this result. Okay? So let me rub this. We'll keep these two reactions. We'll use this result. Let me write this result over here. We'll use this result in our derivations. Concentration of H2A is approximately equal to concentration of A2 minus. We'll use this result in our derivations. Now let us do the derivation. We'll be using this result. Now first, solving for the first equilibrium, we get Kw upon Ka1 is equal to Kw upon K1 is equal to concentration of H2A into concentration of OH minus upon concentration of HA minus. This is Kw upon K1. Suppose we write this as equation 1. Now K2, writing the expression for K2. K2 is equal to concentration of A2 minus into concentration of H plus upon concentration of HA minus. Suppose this is expression 2, equation 2. Now let us divide equation 1 by 2. Let us divide equation 1 by 2. Divide 1 by 2. Divide 1 by 2. The left hand side में क्या आ जाएगा? Left hand side will get Kw upon K1 into K2. On the left hand side we get Kw upon K1 into K2. What do we get on the right hand side? HA minus will be cancelled out. We'll get concentration of H2A upon concentration of A minus into concentration of OH minus upon concentration of H plus. Concentration of OH minus upon concentration of H plus. This is the expression what we get on the right hand side. Now using the result which we had derived earlier, or the approximation which we had used, the concentration of H2A is approximately equal to concentration of A2 minus. The concentration of H2A is approximately equal to concentration of A2 minus. So these two concentrations will be equal. They will cancel each other. Now let us solve it here. Now let me further solve it here. We have got this expression. Now solving it here, let me rub this. Now OH minus can be written as Kw upon H plus. OH minus can be written as Kw upon H plus. So substituting the expression, we'll get Kw upon K1 into K2 is equal to, instead of OH minus, we'll write Kw upon H plus. This divided by H plus. We have cancelled out the H2A and A2 minus. So this becomes Kw upon H plus ka whole square. We'll write this as equal to Kw upon H plus ka whole square is equal to Kw upon K1 into K2. From here we get concentration of H plus is square root of K1 into K2. This is the calculation for H plus concentration for a salt containing cation of a strong base and an amphiprotic anion. H plus is root under K1 into K2. It is the geometric mean of the previous and next ionization constants for the amphiprotic anion. Accordingly, the pH will be equal to half of pK1 plus pK2. It is the average of the pK values of the previous and next ionization constants for the amphiprotic anion. So this derivation is clear. How did we derive? One important assumption we took that in the charge neutrality expression, we ignored the H plus and OH minus concentrations with respect to the Na plus and Ha minus concentrations. That assumption is valid when the salt concentration is not too low. So that resulted in an important result. That assumption led to another important assumption or another important result, that concentration of H2A is approximately equal to concentration of A2 minus. So for a salt containing an amphiprotic anion, for a solution of salt containing an amphiprotic anion and cation of a strong base, the anion ionizes and hydrolyzes in such a manner that concentration of the product on its ionization is same as the concentration of product on its hydrolysis. Understood? Now let us solve some examples based on this. Let me summarize the results first. Let me summarize the results and how to apply this formula. Suppose we have a triprotic acid. Triprotic acid, and we are representing it as H3A. An example of a triprotic acid can be H3PO4, phosphoric acid. A triprotic weak acid, which ionizes in 3 steps. It will first ionize to give H2A minus, then it will ionize to give Ha2 minus, and then it will ionize to give A3 minus. Suppose we have a triprotic acid. It ionizes in 3 steps. The ionization constants are K1, K2, K3. There are 2 amphiprotic species here. There are 2 amphiprotic species here. One amphiprotic species is the H2A minus, and another amphiprotic species is Ha2 minus. For a solution containing H2A minus or a solution containing Ha2 minus, we can apply the formula for pH. Here for the H2A minus, the pH will be equal to pK1 plus pK2 by 2, the average of the previous and the next ionization constant pK values. And for Ha2 minus, the pH will be equal to the average of previous and the next ionization constants. So it will be equal to pK2 plus pK3 by 2. Understood? So this pH expression is independent of the concentration of salt. Whatever be the concentration of salt, the pH expression remains same. Okay. One simple question we can do. Suppose we have given that for H3PO4, the ionization constants are K1 is 10 raised to minus 4, K2 is 10 raised to minus 7, and K3 is 10 raised to minus 11. For H3PO4, the K values are given. What we have to find? We have to find pH of 0.047 molar Na2HPO4, and another question, 0.83 molar NaH2PO4. I have taken 2 random concentrations for the 2 salts. We'll have known that the pH expressions are independent of concentration. So whatever be the concentrations, the value of pH can simply be calculated by pK1 plus pK2 by 2 or pK2 plus pK3 by 2. Now let us solve it. Solving this expression, we get, let us write the 2 salts. One of the salts contain Na2HPO4 contains HPO4 2 minus ions. So the solution will be, first one, Na2HPO4 has Na plus, cation of a strong base, and HPO4 2 minus, which is the amphiprotic anion. HPO4 2 minus is the amphiprotic anion. It is formed after the second ionization. So for HPO4 2 minus, we'll write pH is equal to pK2 plus pK3 by 2. pH is equal to pK2 plus pK3 by 2. What is the value of pK2? K2 is 10 raised to minus 7. So pK2 will be equal to 7. K3 is 10 raised to minus 11. So pK3 will be 11. 7 plus 11 by 2. This is equal to 9. This value of pH is independent of the concentration. 0.047 molar has no role. Even it was 0.5, even it was 0.25, even it was 0.05, etc. Okay, it would have had no role. Only when concentrations is very, very low, then we cannot use this expression. Then we'll have to derive, it will become a complicated calculation. And that is beyond the scope of JEE Advanced, not there in our syllabus. So let's not get into that. Let us understand this calculation first. And similarly, solving for the second one, the salt is NaH2PO4. NaH2PO4 will give Na plus cation of a strong base and H2PO4 minus the amphiprotic anion. For the amphiprotic anion, pH will be the average of previous and the next ionization constants. H2PO4 minus the previous ionization constant will be K1. The next ionization constant will be K2. So for this, we'll write pH is equal to pK1 plus pK2 by 2. The pK1 value, K1 is 10 raised to minus 4. So pK1 will be 4. K2 is 7. So pK2 will be 7. 4 plus 7 by 2, 11 by 2. This is 5.5. So for the second question, answer is 5.5. For the first question, answer is 9. Understood? Understood, everyone? So it's not very difficult. Now, using this concept, you can also derive an expression for pH of isoelectric point of amino acids. That we'll be doing in another video. So thank you, everyone. Thanks for watching this. Hope everyone liked it and understood this concept. Thank you.